Welcome to The Explainer. Today, we're going to crack the code on the invisible rules that run the world around us. We're talking about the gas laws, the science that explains how all the air we breathe actually behaves.
You've totally seen this, right? It's a classic mystery. You go up in a plane, and suddenly your snack bag looks like it's going to pop. Well, I promise you, it is not magic. It's pure science. The gas inside that bag is just following a very predictable set of rules, and today we're going to figure out exactly what they are.
Okay, so to understand the rules of the game, we first have to meet the four key players on the field. Every single time we talk about a gas, these four properties are what describe its situation perfectly. First up, we've got volume. Let's just call this the space. This one's pretty straightforward. It's just the amount of room the gas is taking up. What's so cool about gases is they will always expand to completely fill whatever container you stick them in.
Next, we have temperature, or as we'll call it, the speed. Now, this isn't just about feeling hot or cold. For a gas, temperature is a direct measurement of how much energy its particles have. So, when you heat a gas, you're basically giving its particles a shot of espresso. They start zipping around much faster.
Then, there's the amount of gas. Scientists use a special unit for this called moles. But to keep it simple, let's just call it the crowd. All it's really asking is, how many gas particles are actually packed into this space? Are we talking a small get-together or a massive rock concert?
And our final player is pressure, which we'll call the push. Imagine all those super fast particles from the crowd just constantly bumping and crashing into the walls of their container. All of those tiny individual collisions add up to create one big, steady outward force, and that is pressure.
And this is a fantastic way to see how we measure that push in the real world. This device, a barometer, shows that the air in our atmosphere actually has weight, and that weight pushes down on the liquid mercury in the dish, which in turn is strong enough to support that whole column of mercury in the tube. The height of that column, well, that tells us the atmospheric pressure. Kind of cool, right?
All right, so now we know our players: the space, the speed, the crowd, and the push. So let's get into the good stuff, the simple, elegant rules that describe exactly how they all interact with each other. First up is Boyle's Law. And the perfect example of this is pumping up a bicycle tire. Think about it. As you push the handle down, you are squeezing that air, that gas, into a much smaller space. And what happens? The pressure, the push, inside that pump goes way up, which is what forces the air into your tire. So the key takeaway here is that pressure and volume have an inverse relationship, as long as the temperature stays the same. That just means when one goes up, the other goes down. You cut the space in half, you literally double the push. You double the space, the push gets cut in half. Simple as that.
Next up, we've got Charles' Law. And if you've ever seen a hot air balloon just majestically floating in the sky, that is Charles's Law in action. The crew uses a giant burner to heat the air inside. As that air gets hotter, its particles speed up and they spread out, causing the gas to expand and fill that massive balloon. That makes the air inside less dense than the cool air outside, and poof, up it goes.
So this shows us a direct relationship. As the temperature, the speed, goes up, the space the particles need also gets bigger, assuming the pressure stays the same. And the opposite is true too. If you've ever taken a balloon outside on a cold day and seen it shrink a little bit, that's Charles's Law.
Now for Avogadro's Law, and this is probably the most intuitive one of them all. I mean, if you want to inflate a balloon, what do? You blow more air into it. You're increasing the amount of gas. You're making the crowd bigger. And so, of course, the balloon has to expand to create more space for all those new particles.
But here is the really mind-blowing part of Avogadro's discovery. It doesn't matter what kind of gas it is. It could be helium, nitrogen, methane, whatever. If you have the same amount of space at the same temperature and pressure, you will have the exact same number of gas particles. A bigger crowd will always need more space, regardless of who's in the crowd. That's pretty wild when you stop and think about it.
Okay, so we've seen how these players interact in pairs, but what happens when we combine all of these simple rules into one single powerful super equation? This is it, PV equals nRT, the ideal gas law. This beautiful, elegant equation is one of the absolute cornerstones of chemistry. It connects all four of our players, pressure, volume, the amount, and temperature, into one master formula that lets us predict how most gases will behave under most normal conditions.
So let's break it down one last time with our nicknames. It shows that the push times the space is directly related to the crowd times the speed. And that letter R,
That's just the ideal gas constant. You can think of it as the special glue that makes sure all the units in the math work together perfectly in the equation. But why? Why do gases follow these rules so perfectly? I mean, knowing the laws is great, but understanding the reason behind them is even better. To answer that, we need to zoom way in and look at how the individual gas particles themselves are actually behaving.
This whole idea is called the kinetic molecular theory, and it explains everything with 5 really simple assumptions. It just imagines gases as being made of tons of tiny, fast-moving particles. These particles are so small their own volume is basically zero. They fly around randomly, they don't attract or repel each other, and when they do collide, they just bounce off each other without losing any energy.
And this graph right here, it illustrates that 5th rule perfectly. Just look at the blue curve. That shows the speeds of gas particles at 0 degrees Celsius. The red curve shows that same gas, but at 100 degrees. As you can see, increasing the temperature gives the particles a much wider range of speeds and a much higher average speed. It is the engine driving all the laws we've just talked about. So, there you have it, the simple rules that govern the invisible world of gases. Now, we've learned the ideal rules, and they're based on the idea that gas particles have no size and don't interact. But what happens in the real world, when pressure gets super high or temperatures get really low? Do they start to break the rules? Well, that's a story for another time.